velocity here. So we calculated the average dipole moment oriented along the z direction. And so what we have then is that using this energy of interaction between the dipole and the external electric field, we evaluate that the average dipole moment is equal to P0 times this Langevin function, which is given by this. Alpha again is P0 E over 2 Boltzmann T. So I either increase the electric field with respect to T to make alpha large, or I decrease the temperature T for a fixed alpha E, right? But if E is small, right, at room temperature, right, then what happens is that you have room temperature here, so if you change E all the way to 0, then you get the induced dipole moment should go to 0. If there is no electric field again, there is no induced polarization. We cannot call it induced dipole here because the polar molecules already have a permanent dipole, except that they're randomly oriented. So then when you apply the electric field, you align these, and then you have a polarization vector that is not equal to 0. Okay? Polarization, remember, for us, is the dipole moment per unit volume. So I have many of these sort of things, right? So it's proportional to this. So it's kind of interesting that you can actually do this, that in table 6, what was it, 1, they have what the alpha over 4 pi epsilon 0 is in units of 10 to the minus 30 meters cubed, right? So you also have what P0 is for these molecules, okay? So the P0s that you have, they're measuring what they call debye, and a debye is, they give you what that is 3.334 times 10 to the minus 30 coulombs meter, okay? So for water, say, P0, this is for water, is equal to 1.05 this debye, and that 1 debye is 3.34 times 10 to the minus 30 coulombs. Okay. This is what they'll give you in this value. So then for water, 1.48. So let's tell you what P0 is, right? So then if I imagine, well, how we're measuring alpha, so you have a table of alpha over 4 pi epsilon 0, and the units here are volume. Volume of 10 to the minus 30 cubic meters, right? That is where in table 6.1. So in some sense, by measuring, or by finding what alpha is, and divide by 4 pi epsilon 0, you get a quantity that should go as the volume cube, which in some sense it should be proportional, if you think about it, of the volume of your molecule. Right? That's what it is. And so they give you, they don't tell you what these are, but there are molecules that have very large coalescibility. And the reason you might say, well, how come they're large coalescibility? Well, they're large molecules. Hemoglobin and so on they have a very large P0s, right? So then if you do this back of the envelope calculation from this P0 that I have here, which is given in terms of this debye, which is 10 to the minus 30 coulomb meters, you then you have this P0, you have the polarizability, which is P0 squared or 3 kVolts T. At room temperature, I can do kVolts T to be 0.025 dBs, right? I can then put P0 squared, and I divide this by 4 pi epsilon 0 to get a volume, and it turns out that the volume should be of the order of 19 angstroms cubed, and T equals 300. This is for water. Hot. 300 Kelvin is not hot, it's room temperature. Remember, it's Kelvin. We're doing Kelvin, which is 0 degrees is 273.16 Kelvin. 0 degrees centigrade. So this is what we get from that molecule. Okay, so what are we getting out of all of this? Out of all of this, what we're getting is that the polarizability, I can always write that a P that is induced is really proportional to alpha and proportional to electric field E. Okay? And so what we're saying is, oh, I have this relationship, and for different substances, I can use different models and evaluate this alpha. Clearly, what we want to do is to be able to calculate the alpha from first principles before we do anything. That's what we mean, right? So this is a simple model. In solid-state physics these days, we can do a lot better than this, okay? I mean, this is a very simple model that we can actually go into right now in terms of this. So let's go on to a picture that came from Faraday. And now let's imagine that I have my capacitor. So let's go back now to capacitors. Before we do anything. So imagine now I have a parallel plate capacitor, and I have a sigma here. And a sigma there is minus the sigma that I have, of course, on top. And this distance here is B, and I have placed now inside this thing a conductor that has a